So good morning, everybody. Welcome back to the second day of the conference. And we are very glad to have Professor Tschinkel with us. A year ago, when he presented some of the results he had on equivariant birational geometry, I look at them and then I told Ludmila and Ernesto, this is a subject to make a conference so that we have algebraic geometers and algebraic topologies together so that they see the similarities they're doing, what can learn from one from the other. And I was very happy when I invited Professor Tschinkel and he agreed to come with his students, postdocs, and his collaborators. So we're very happy to have you. Professor Tschinkel is a professor in the Courant Institute, also works at the Simon Foundation, leading the mathematics and physics office. And he will be opening today's lecture. Professor, good morning.
Thank you so much. I'm delighted to be here. It's always a pleasure. And I'm also looking forward to learn more about actions of finite groups in the context of topology and algebraic geometry. So in algebraic geometry, we're interested in algebraic varieties over some field. And for the purposes of this talk, the field is algebraically closed, characteristic 0. And when we see a variety, we look at its function field. It's an extension of the ground field. In particular, we are interested in varieties that are rational. So the function field is a purely transcendental extension of the ground field. The variety is birational to projective space. And then when you have a field extension, the Galois theory tells you, well, let's look at automorphisms of the field that do nothing on the ground field, and in this context, we're looking at automorphisms of the function field, and this is a group of birational automorphisms of the variety. And in particular, we would like to understand what kind of finite groups can we have that act on rational varieties. So, in particular, one of the basic actions of a finite group on a rational variety is a linear action on projective space. The linear action means you have an action on projective space that's induced by some linear representation of your finite group, spatial representation. Okay, now when we talk about birationality in algebraic geometry, we can, of course, ask about isomorphism of function field, the dependent notes of birationality. We can look at birationality in presence of additional structures. As you're thinking about finite group technical varieties, we would then look at G varieties. G a priori is a bit of birational automorphisms, but you can pass to a model where the action is regular. Another version of birationality that you might look at, you can look at a field together with some extra structure. Or if you think about varieties, you can look at a variety together with the volume form where n is the dimension of the variety is logarithmic poles. All right. Or you can look at a field together with some Asumai algebra over it, which would mean a variety together with some sheet of Asumai algebra, so the the Brown group, if you like, and then you could ask about birationality in this context. What would it mean? I mean, it just means what it says. For fields. All right, so the flavors of birationality, as I mentioned, of course, you would like to understand when is the variety birational to projective space, when is it stably birational to projective space, that is after multiplication with Pn or some n, or if you are thinking about G varieties, then you may ask, well, is my action linearizable, which means that it's birational to linear action on Pn, or is it stably perhaps linearizable, which means you multiply with projective space, but this trivial action. And then you ask, is that product perhaps birational to Pn, this linear action? And in the context of varieties with additional structures, you now consider pairs consisting of a variety together with a form, the logarithmic poles, and again, after birationality. And then your reference variety would be projective space, of course, Tn, with a standard form that you can put on it, like dx1, which dxn over n. So standard volume form is logarithmic poles. So looking at these equivalences on algebraic varieties with such structures, you can introduce 3 abelian groups on these equivalence classes. Let's say Bern NK is a 3 abelian group on birational birational equivalence classes of algebraic varieties of dimension n over k. The ground field is also important. Or when we talk about G varieties, we can look at Bern Gn, Bern and Gk, birational equivalence classes of G varieties. So now we're looking at birationality that reserves of the group action, or I'm writing it like volume in bold-space to emphasize that it's volume. Abelian group on birational equivalence classes of, let's say you can do G varieties, Bern and Kg, or simply varieties without a G over K equipped as a volume form of logarithmic poles. I mean, G could interact with the volume form if you like. Or you can look at varieties with some I algebras. You can look at stacks, and again talk about the rationality of stacks and look at 3 abelian groups on that.
Some algebras wouldn't be a subset of stacks fully natural. Or...
Yeah, something like that. So, again, so you have to, of course, be very careful. You don't want to place a moduli state generic point. You have to be very careful about the notions of rationality for stacks. But now, why these 3 abelian groups that I've introduced, why they're interesting at all? I mean, we're not learning anything, we're just deciding from this equivalent, and then, okay, everything breaks up into these classes. Well, of course, basic operations include varieties. Taking a product will give you a ring structure on these things. And it turns out that already, as defined here, there is a very intricate internal structure coming from non-trivial stable birationality. So there are examples of varieties, complex varieties in dimension 3 that are not rational, but are stably rational. So you multiply this projective space, and then suddenly you are equivalent to something else. And so that, of course, somehow gets reflected in this rather rich structure. Now let me start this group, the group of equivalence classes of varieties with a logarithmic volume form. This is a recent joint work with Antoine Chamberlain and Couttage from this year, from January. All right, so the right pair brackets for the class of pair. Now let's look at some examples. So what do we have in dimension 0? In dimension 0, of course, you have a point, spec k, and what is our logarithmic form? It's some number, so t minus 1. Okay, now what about dimension 1? In dimension 1, we can look at t1, and it's like that's the standard thing that you would take there would be like dx over x, dt over t. And of course, when I say logarithmic poles, it's at most logarithmic poles. So something without poles is also fine. So I can take, hypotenuse curves and things like that. All right. Now, as I said, a priori, when you have such a thing, it defines these classes, so what are you learning? But when you see something with logarithmic poles, you naturally think, okay, there is the interior where I have no poles, and then there is a boundary where I'm going to pick up poles. So let's try to organize the data. Of course, since we're interested in birationalities, we can look at models where the polar divisor is normal crossings, and the union of components, the reducible components, the alpha. And then, as always, we look at strata. We're taking intersections of all these components. It's called a dA. And then, having a form, a volume form with logarithmic poles, you can take residues along the strata. You take a residue, again, you get a form like this. You can continue taking residues. So for each stratum, you have like an iterated residue. Now, of course, people who've done residues know about orientation. I mean, they know that here and there it's not quite the same, but you will see that in our formula, orientation doesn't matter. And so it turns out that passing from the generic points, so to speak, of your variety to generic points of strata, you can cook up homomorphism from burn n of k to burn n minus 1 of k by doing the following. Well, it's sort of an iterated plus minus, it's sort of a sum over all these iterated things. But of course, each time you take an iterated residue, you sort of drop dimension, but you want to end up in n minus 1 dimension. So you bump up the dimension by the standard class that I gave you, the class P, which was P1 with dt over T. And so that now the dimensions match, and you actually have something like this. So this is a map that you do in general. Now the question is, why is it a well-defined map? Why is this compatible with birationality? So you have to do your blow-ups that you use, of course, featurization, and then you have to check that this definition is actually a well-defined homomorphism. Now you're beginning to see how to distinguish classes as burn n. Well, because sometimes this homomorphism will allow us to compute something on the strata, which will be relevant. I'll give you an example. So we'll look at P2 with the standard thing, dx1 over x1 dash dx over x2. Or we can look at P2 with, let's say, degree 3 curve n. And then, of course, when you specialize to the boundary, it makes a difference whether or not you see 3 lines or you see genus 1 curves. The function fields are not the same. And, well, of course, in this case, you would say, oh, but that's trivial because I can do it just by elementary birational geometry. I understand everything about surfaces. But now something like this you can do in higher dimensions. And as you can imagine, you can have much more complicated arrangements on the boundary. And so this homomorphism is already very useful when your standard birational techniques start failing you. All right. But it turns out that actually it's a derivation. So the square of it is 0. You can write a complex if you like. You can try to compute homology of the complex. We haven't done that. But, well, one of the properties of this thing that you can write down. Moreover, as I told you, there is a product structure. And look what happens when you try to apply the derivation to the product. I mean, it looks like a derivation. Forget that epsilon. Epsilon is just a sign. So of course, sign, that's fine. So basically it's, derivative of A times B, derivative of A times B plus A times derivative of B. That's fine, that's okay. But look at what people would call a quantum deformation. T times dAdB. So T is the class of T1 in the standard form, comes in, if you like, as a formal parameter, any way you want to think about it, but this is a formula that we have. Okay. So I hope I convinced you that already that the first steps here, sort of an interesting piece of structure in birational geometry. But actually, playing with these groups, you can get much more down to earth geometric applications. For example, we can look at birational maps, that means whose projective varieties over K, X to Y, and we can cook up an invariant of that map by looking at the sort of components, the visorial components of exceptional locus of the map or its inverse. And then we can look at the difference between these two, but now consider as well classes of function fields, so basically just keeping the generic points of these components, and plus and minus depending on where you are. And this recent theorem of Lin and Schindler says that well actually it's a homomorphism. So when it respects composition of birational maps of varieties, and that allows to answer the question that when we saw this, together with these geometric applications, we decided that, well, surely it's such a universal thing. It's going to work in the context of G equivariant birational geometry or orbital context. And so there's sort of a straightforward generalization of this. You write down the same formula, you just need to check all the properties. You need to check about these things and the properties of the corresponding Burnside groups, and the equivariant Burnside group, another Burnside group. And when you do this, you obtain sort of information about the structure of the molecule in particular, but also about centralizers of finite subgroups if you need equivariant context, because this is what it is. Another direction, another sort of application of these ideas is specialization. So it goes back to the work of Platonist. If you have a family of, let's say, threefolds, Farnell's threefolds, a smooth generic fiber, and you look at special fibers that is allowed maybe to have small singularities or not, then the basic obstruction for rationality, namely that the media Jacobian not being equal to products of Jacobians of course, that's specialized. And so if you find that in the specialization that the media Jacobian is not what you want, I mean what you want, so the media Jacobian producing an obstruction for rationality of the special fiber, then before the specialization already had that. So that was the idea, it worked. And in particular in Bouville's paper, he used this to prove non-rationality of some classes of Farnell threefolds with this method. Now, the advantage of this method, why is this interesting, is that computing explicitly the intermediate Jacobian and proving the relevant geometric facts about the intermediate Jacobian is not so straightforward in the generic fiber, but the special fiber, if it happens to be, it has some additional structure. In particular, Bouville was specializing to conic bundles. And once you have a conic bundle, then the theory of intermediate Jacobians on conic bundles is much easier. So the criminal of the discriminant curve, which you see, it sort of stares at you, and it's much easier to prove for that variety, the failure of the intermediate Jacobian being one of the Jacobians of curves. And so that's how the idea played out. Now, so that was known for many, many years. What was not known is how to deploy it in sort of other contexts. And because Bazin, who had this great idea to use something from the theory of algebraic cycles, going back to the work of Bloch and Srinivas, namely the integral decomposition of the diagonal, which was then developed by Kurotel and Pirotka into universal Chaldean triviality. So these are all properties of varieties that they showed to specialize well in families with mild angularities of special fibers. And again, the idea there is that while you don't have any obstructions of the general fiber that you can see or compute, in the special fiber, you can do it, take the conic bundles in dimension 3, ended up being sort of a universal class of varieties to which you want to specialize. And then Schindler proved specialization for stable rationality based on work with Larsen and Lutz, and then Maxime and myself, and I've talked about this here already, and the best showed it directly for rationality using the Burnside group formalism. And so once you have that in place, once you realize that, well, you can specialize and then play this, the special geometry of distinguished varieties, you get wealth of new results in birational geometry. You can prove failure of stable rationality in situations that are totally inaccessible before. And then you get into these things where you start looking at how these different classes, let's say, of Panos threefolds connect to each other. That is all work of Ludmil and collaborated with Janowski, where they showed that the way they put it, there is some kind of plate that we can go from one class of Panos threefolds via some singularities to another class of Panos threefolds, to another one, to another one. So everything becomes sort of connected, and then you can use these singular ones, these mild singularities, to show, for example, that all Panos threefolds either they're rational or birational to a cubic threefold, For the ones that are not rational, the very general one is not even stably rational. This is what you can get with this specialization technique. And again, so I want to emphasize this. The reason this is interesting and working is that in the special fiber, you get computable abstractions to stable rationality. And this is how to disprove stable rationality of the general fiber. But actually, you can use this technology to go the other way. When you do high dimensional geometry, very often you run into a situation where you want to assume that some loci are in general position. And this is typically a big headache because, well, very often they're not in general position. And you want to use those loci to prove, let's say, something, rationality. And in the previous technique, in the classical case, what you would do is you would analyze every special case, and in every special case come up with some ad hoc rationality construction, which can be very, very time consuming and sometimes even not possible. This method allows you to conclude rationality without going through all of these constructions. In other words, you can first sort of deform to the case of a very general position for the loci that are supposed to show that some threefold, fourfold is rational. And then you can specialize. So if you know that for the very general sort of situation where all your cycles that you need are in general position, you have rationality, then you don't need to produce an explicit rationality construction of the special fiber. You get it for free. And that's sort of a miracle because in many cases, they don't even know how to do it. People are fighting with this for cubic fourfolds for a long time. You have a smooth family, and what happens if something begins to collapse and becomes special fibers in a smooth family. So now, how do we do this specialization of rationality with machine learning? We'll go through this in detail. So now we're thinking we are over function disk, DVR. We have some function field. We have a smooth projected variety of interaction field of some dimension, relative dimension, and if you look at some model. Now, the model has special fibers, and the special fiber is again a union of divisors. Sometimes there are multiplicities, but it turns out that we can ignore them. And so now we write down a formula that would map the Burnside group over sort of the generic point over fraction field to the Burnside group over the residue field, and look at this formula. The only thing that I changed in this formula was instead of T, I put an L, where L is simply the class of the affine line. It's just an additional variable. It's not sort of a random coincidence. This is exactly what I'm doing. So the Burnside group is volume forms. Gets deployed here, if you like, in this case. In other words, you should think of the class of an affine line like an integral. So this formula is, of course, as I explained from previous conferences, is basically integration. So you're integrating, and you're just saying that the integral does not depend on the way you complete your variety, because it's an integral, so it doesn't matter whether it's an open or a closed interval, the answer is the same. But the fact that you can express the answer in terms of a boundary certification, and that you get geometric information from the boundary certification, that's a miracle. And so what actually happens in this specialization, okay, you have a family and you have a special fiber that's the divider. The way we are thinking about it is that actually before we work in the relative situation, we work in the absolute case where we have a variety with a boundary. And then we have some kind of map that goes from the generic point volume form to the boundary. And then all we do is you just turn it around, and that's it. And then you get the specialization. So the moment you have this thing in your head, that there is some birational variant like this in the absolute case, you can do it in the relative case. And so as you can imagine, you can do the same thing in the presence of G actions. You can do the same thing for stacks, you can do the same thing for orbitals, and so on and so on. So you get a well-defined homomorphism of abelian groups. And just the existence of this homomorphism allows you to prove this kind of specialization for mild single relation. So, and as I already said, it's essentially the same formula as the one for this derivation in the Burnside group with floating points. All right. So now, last year, I published the equivariant birational types. You can do it in presence of G actions. You can do it for these logarithmic volume forms, where again, it's sort of a meaningful specialization result. That's from January of this year. You can do it for orbifolds, as we did last year with Andrew, and so on and so on. Now, let me discuss the equivariant Burnside group. So, where we look at varieties with G actions, equivalence classes. And again, to understand these G actions on the generic point, on the function field, we would like to have a similar notion of some kind of boundary, some derivative, where you would extract information from a boundary. Now, all right, so how do we do this? Well, again, we can assume that we're looking at a very nice model where the boundary is normal crossing. Again, we have this boundary certification. But what's the boundary? Well, the open piece would like to be the piece that the group action has no fixed points. No element, free action on the open. And then the boundary dividers, well, we'll have some stabilizers with no reciprocal groups. And actually, the standard model that we want, there are different ways of saying or postulating what a standard model should be. This is a little bit more restrictive than necessary, but we require that for every component of the boundary, either the group translates this into a disjoint component, or it preserves the component. It acts on the component. All right. So this is the standard form. Goes back to Reichstein-Usen. And once you have such a form, it turns out that all stabilizers that you have are abelian. All right. So now we have a set of divisors. It's non-trivial, so cyclic stabilizers. Let's call them H alpha. And of course, what happens is that, okay, you have a group action. So particularly if you have an orbital divisors, if you now know they are disjoint, those divisors, right? So, well, which element of the orbit do you pick? They all look the same, so to speak. Of course, when you put another element in that orbit, the stabilizer will be conjugated. So you have some kind of conjugation action in place. And so therefore, you now look at these cyclic H alpha stabilizers up to conjugation, because you don't want to prefer one particular representative of an orbit. So there's some natural conjugation relation. And as I said, some elements of the group could act on the divisor or the stratum. Okay, so that gives you a subgroup in the centralizer of your stabilizer, modulo stabilizer. All right, so that's what I call the residual action. So now I can do the following. I know that I'm doing sort of birational geometry. So I can look at those divisors of the boundary that I cannot obtain by blowing up. What do I mean? I mean, I know that my exceptional divisors, when I blow up, well, realizations of normal bundles, I mean, there are uniruled and things like this. So if my divisor is a non-trivial stabilizer, not uniruled, it will be present on every model. It's not going to go anywhere. So I can extract some divisors in the boundary that are fashioned in this way, not obtainable by blowups, together with the action, of course. So, and we call these incompressible divisors. And so then, having a group action, G on X, I can write down sort of a formal thing, let's say the incompressible class, which is simply a formal sum over the stabilizer up to conjugation, these H alphas up to conjugation, of Y alpha acting on the function field of that stratum. And well, I have a cyclic group. I have sort of a B alpha, which is a character of the cyclic group in the normal bundle to the divisor. That's a symbol, and I just write it down like this. So, all right. I keep the stabilizer, the divisor, the generic point of the divisor, the residual action, and the character. Yes.
Can you say a word? Why are these stabilizers cyclic?
Why is it? What else can it be?
No, I don't know.
It's divisor. Yes, you have to. Yeah, that's not a choice.
Yes, I think
The group action generic is really.
would was this type of thing.
Yeah.
I'll ask.
You have a generically free action of the whole variety. The action has to go somewhere.
Okay.
Yeah. All right. So we have this class, well, it's a real Boolean group generated by symbols as above, and of course, so it's a well-defined birational variable. Because I can't create these kind of things by blowing up by definition these classes. And so, well, let's look at what happens in small dimensions. So we're looking at these divisorial symbols. So stabilizer, action on the divisor, and in dimension 2, divisors are curves. And of course, if I have a curve of units at least one with non-trivial stabilizer, when I blow up my variety, it will persist. It will just be carried from one birational model to another model. It will always be there and always be there with that stabilizer. Well, there's nothing you can do with such a curve. But it turns out that even genus 0 curves can give rise to incompressible symbols if the residual action on that curve is not cyclic. You cannot create such classes by blowups, because when you live on a surface, and as I said, you understand the model of a surface, all the stabilizers are abelian. So you have an action of an abelian group in the tangent space to your distinguished point. So when you projectivize, you get, of course, a T1, but the induced action is cyclic. And as soon as you have, let's say, an S3 action on Q1, then that class is going to persist on every model. That physical rational curve with that residual action. And so you keep that. Now, let's look at what happens in dimension 3. So now we're looking at surfaces. Of course, the surface is not uniruled here in business, but you can also have a rational surface, like a cubic surface, with no trivial cohomologies. You cannot create cohomologies by blow. So, or the y-action is not equivariantly birational to what you would get when you blow up smooth rational curve in the threefold. Again, and you know that your surface is the residual action is not birational to a principal surface, well, then you win. For example, the S4 action on T2 is not equivariantly birational to something that you can obtain by blowups. So it's a very, very rough invariant. You would think, well, how on earth can I extract anything from it? I mean, it's so basic, so rough. But then it turned out that already in dimension 2, you can prove new results. They're not immediate with standard birational geometry techniques in dimension 2. In fact, linear actions in dimension 2. Subgroups of PGL3. You can have the same group acting differently on P2 in a non-birational way, and that wasn't visible before. So how do you do it? You take S3, you take the two-dimensional representation, you twist it by a character of a cyclic group, Cn. You look at the projectization of the trivial plus this twisted two-dimensional representation. So you get an action of the group Cn times S3 on P2. Now, where do we see issues? Where do we see sort of these classes? Well, one class is staring you in the face, is the projectivization of this V times chi. And of course, chi goes away. That means you get a stabilizer, Cn, and then you have an induced S3 action on P1 with the character chi. But the other thing that stares you in the face is that there is actually a fixed point on that P2 for the whole group. Now the group is not abelian, so we have to pass to a standard model. It's only on the standard model that you can do the class. When we pass to the standard model, we blow up. So we blow up, we projectilize, on that exceptional Q1, you get an S3 action, and the stabilizer is again the cyclic group Cn, except that the character now is minus the character. So in particular, if n is big enough, let's say 5, and the character that you pick for one action is not equal to plus minus the character that you pick for another action, you get yourself an action, two actions of the same group that are not birational. And that's sort of an example that you can then put into higher dimensions. You can do something like this in 3 and 8 dimensions. In particular, of course, we were discussing Ron and others. I mean, how do we, now that we have these invariants, finally classify all conjugacy classes of linear actions in the plane primordial? But as I know, it's still open. Maybe you guys have made some progress on this, but it's still an open problem. All right. So birational rigidity techniques, the main tool to distinguish G actions previously. These techniques don't work well when the group has a fixed point, because it can blow up and you have to keep track of all the fixed points and all the low side. The action works, I mean, the technique works well when the action is large. And so in case of P2, primitive, and then you can distinguish. So then you look at these large orbits with the special loci and so on and so on, and simply say that nothing can be done. But in the cases that we are looking at, there are actually many birational models, equivariant birational models. And well, how do you know that you can untwist it and some other models, and so on? But the tool that we have is actually pretty good. So now you can think about other varieties. So dimension 3, I mean, as I mentioned, we can do P3 with actions like this. How about the 3-dimensional quadrant? So the rational geometry of 2-dimensional quadrics, equivariant birational geometry was completely settled. Stable birationality, Brendan and I have settled last year. Even for P1 times P1, even for quadric, that was an open problem. But how about a 3-dimensional quadrant? Now, of course, you are over algebraic closed field, complex numbers. So we have the standard form, and there are some obvious finite groups that there is on the face. You can produce the variables, or you can switch signs of the variables. All right, so you have some subgroup of the group of D5. Now, if you have a fixed point for the action, then of course, projecting from the fixed point gives you linearizability. It will be birational to P3. So we'll assume that the group that we're looking at, the full group, doesn't have fixed point. On the other hand, having a fixed point for an abelian group is an equivariant birational invariant. So we will always assume that when we restrict to abelian groups, we have fixed points. All right. So these are the two things that we will assume. No fixed point for the big group, fixed points for all abelian subgroups. And then we just enumerate the groups that we have. Okay, you start looking at these groups. So these are the groups. And then we can ask the question, well, for each of these examples, does our Burnside formalism allow to prove non-linearizability of the action? So, and it turns out that those examples in red are actually obstructed from being linearizable. And for the others, we simply don't know. And Derek and Chelsops, they proved that the S5 action, I think, like the paper that we posted just 2 weeks ago or so, 3 weeks ago, the S5 action is not linearizable. And then I guess, well, what about D5? What about Q8 or D6? Small groups, linearizable, not linearizable. In other words, if you're thinking sort of numbers theoretically or non-closed fields, that when is a quadric rational? Well, it has to have a point. So, but in this context, you don't have to have a fixed point to be linearizable, the analog of rationality. And so, okay, you have all these groups there. Can we make the quadric irrational without the standard rationality construction, which is projection from a fixed point. Can we have a situation where the thing is generalizable without the thing that's obvious? And well, we'll have an answer hopefully at some point. But the incompressible symbols allow sort of to eliminate at least these red cases. There's some progress here. All right. And so this is a theorem that I mentioned that if you have a smooth quadratic over C that has 5 actual computational variables, then it's not linearizable. So we've eliminated, the blue one is not linearizable, the red ones are not linearizable with the Burnside formalism, or what about the other? Okay, well then we can look at some other examples. We can look at the Segre cubic threefold, the singular cubic threefold. It's and you look at bar, 6 points for the lines. Well, it could be 3 going up in points and the lines, and then you have the S6 action on it. There are 2 S6 invariant divisor classes, the quartic and the canonical one, the Segre cubic. And then you can say, well, so you have an S6 action in this situation produce variables. For which subgroups do I have linearizability? The rational variety, when is the thing linearizable? So, well, it is known that the A6 and S6 actions are birational rigid, but the situation with A5 and S5 is actually very interesting because there is sort of standard embedding into S6 and a non-standard embedding. Okay, there are 2 A5s and 2 S5s in A6, and it turned out that the non-standard actions are linearizable. And it's actually not difficult to see because if I told you this thing is a blowout of P3 in 5 points. So how do you access this 5? You just produce the 5 points. So that's linearizable. But the standard actions are birationally rigid. So that's the result of envelope. In particular, you have these A5 actions of the same variety. One is linearizable and the other is not birationally rigid. So there are 2 results in this direction. So first of all, we show that these are stably equivariant birational actions using universal torques, and again, I presented this in the previous conference. So they are not birational, but stably birational. These actions, and in particular, stably linearizable. But then you can ask, okay, which other groups can we look at? And it turned out that there is actually an action of C2 times A4 and D4 that's not linearizable in this context. Again, you can enumerate all the groups. You would exclude groups which would have a singular point of the Segre cubic with a fixed point. There is some list of groups. You can write them down. And well, so I should mention that the result by Reichstein and collaborators was the fact that there are forms of M06 bar or those fields that are not rational. You can actually do homology for the six actions, so on and so on. But as you go to smaller and smaller groups, I mean, it's sort of. So, well, in the same vein, let's look at other very symmetric rational threefolds. You can look at what's known as the Burckhardt quartic. The Burckhardt quartic, to take this elementary symmetric polynomials, now at degree 4, degree 1, and 6 variables. Okay, you get a very, very symmetric threefold that's rational. And you can ask, well, what about linearizability of the action for some subgroup of S6? So suppose you have an involution that's just like 1, 2, it changes 2 of the variables. All right, so let's look at what is the fixed locus for that involution. It's going to be a quartic surface without singularities, PC surface. So now that we are informed by this formalism that if we have a divisorial class that's not union ruled, it's incompressible, it will be on every model. So as soon as we have this, we can look at, how does it compare to linear action And it turned out that when you compute classes in this kind of group of linear actions, you never get non-unilateral classes at all. So in particular, you're guaranteed that the action is not going to be linear. So the moment this involution is in your group, that's it.
Is it obvious this case is smooth?
It's a singular, 12 singular point.
But minus.
Yeah, exactly. So, so that's a class. And so these symbols cannot arise from linear actions. So this is sort of a very simple application of that very, very rough invariant. And I'm not sure whether or not people doing this properly. Now, of course, when you classify involutions in the three-dimensional Kremlin group, taken by Prokhorov, the class that we're looking at, it actually shows up. It's a special case in his classification of involutions. You know, he gets smooth K3 surfaces in general, like a singular one, and so on and so on. So I hope I was able to show you how this formalism of these incompressible symbols work. So now I've explained, extracted very rough invariants, but now let's look at the full thing when we keep all the information presented to us. All right. So the full Burnside group is going to be generated by symbols H, an abelian subgroup of G, Y acting on some function field K, and beta, string, a collection of characters of H. And Y is the subgroup of the centralizer on B of H over H. The residual Y action on some function field of transcendence degree at most n, and then a sequence of characters of H up to order. In particular, when I write sort of such a symbol, I also keep the symbol with a trivial stabilizer. And I look at the generically reaction, I do have a contribution from a trivial stabilizer, and that would be the generic point of the whole variety of the residual action Y would simply be the G action of the function field of the variety. So the symbols will be subject to conjugation and blow-up relations. So conjugations, as before, simply if I pass to another representative of the orbit, I have to conjugate. And then the blow-up relations, there is one very obvious, very trivial. If two of your characters add up to 0, the symbol vanishes. The non-trivial relation is this one. Namely, a symbol is the sum of two contributions, depending on the string of characters that goes into the symbol. So if two characters coincide, the first one, theta 1, is 0. And otherwise, it's the sum of two such symbols where the stabilizers H and H are the same. The residual action is the same. The only thing that changes is, well, these two characters, B1 and B2, get replaced by B1, B2 minus B1, and then B1 minus B2, B2. That's it. That's the relation. The second one, the second contribution, again, it's 0 if the BI is in a subgroup generated by B1 minus B2 for some I, and otherwise it's some action. I change the stabilizer, residual action changes, the field in the middle changes as well. The function field, it gets an extra variable, and the string of characters gets shortened by 1. To understand this, you have to look at what happens when you blow up a point on the surface. So we are on a smooth surface, we have a point, if we said to understand the model, the stabilizer is abelian. So what happens when you blow up a point with an abelian stabilizer? You get an exceptional divisor. On that divisor, on that P1, you will have two fixed points. The two fixed points, the weights will be precisely those, B1, B2 minus B1, B1 minus B2, B2. So the contribution to theta 1 is what you see on the exceptional divisor, these two fixed points for the group. And then, depending on how your characters are aligned, like B1 and B2, you could get a residual action, you could get a non-trivial stabilizer on the exceptional divisor. The moment you get the non-trivial stabilizer on the exceptional divisor, that's the second kick. That's when this other symbol kicks in. This is the stabilizer of the exceptional curve. And the residual action on it, well, whatever is left on that P1, you could still have an action. Trivial, but whatever. There's something that's going to happen there. And then, of course, the string of characters. Previously, you were recording the two characters of the Wheeler stabilizer in the normal bundle tangent space at the point that you go up. And in the end, the exceptional divisor, the normal bundle has only one character in it. And that's the one character that you record. And it turns out that this simple model encodes everything. In other words, when you now define the class of an action on a standard model as a sum over conjugacy classes of abelian subgroups or function fields of strata with non-trivial stabilizers, together with a collection of weights of the stabilizer of the normal bundle, so that's a construction, and U is as an element in that group generated by symbols modulo those relations, then you get an equivariant birational variant. So again, the symbols record generic eigenvalues of H in the normal bundle along F, the induced action on the function field of F, and the stabilizer. So, and that's a theorem with Andrew Kresch and myself. It's well defined. The assignment is well defined. It's not quite the burn that I put on the very first and second slide, maybe. On the first slide, I just said equivalent classes of algebraic varieties of dimension n is GX. But actually, it's contained in this formula. Those correspond precisely to sync to stabilizer 1. So I can simply forget all the other symbols in the action representation. If I keep only one summoned in this formula here, H is 1, then I get precisely the groups that I had before. But I want to sort of encode all the information that I have about the action. And this is what I get. Now, I don't know, people doing actions of finite groups in other contexts, presumably, yeah, so they've seen something like this, but in algebraic geometry, this is sort of a new construction. And I showed you applications where we keep only part of the information, but there are also interesting applications where you use all the other pieces. So let's look at the crucial relation B2 and let's try to understand what exactly is preserved in this relation. So the observation is that let's look at the middle piece. So we have sort of a residual action on the middle piece, like on that stratum with non-trivial stabilizer. And what kind of geometric information can we report about the stratum? Well, for example, look at the MRC quotient, maximal rational connected quotient, the dimension. The variety could be rational connected or not. So if it's rationally connected, MRC quotient is dimensional. Not rationally connected, there's something there. And it turns out that that relation, B2, doesn't change that property, because remember, how did we get the relation, the theta 2 term? It was just adjoining an extra variable to the function field. So it's just taking a variety product with Q1. So if there was some dimension of the MRC quotient that was being carried along, the product with Q1 is not going to change that. So that's telling us that the Burnside group allows a direct sum decomposition into pieces where, for example, you focus on a certain dimension for the MRC quotients. Or ununified cohomology. You can look at H1, Y acting on the Picard group of some model of your stratum. I read D, but it doesn't have to be whatever it divides, it's just a variety. There's an residual Y action. Well, again, ununified cohomology, the Brouwer group does not change when you multiply a variety with P1. And so if you had this cohomology initially in the Y action on K, you will have the cohomology in the Y bar action on K of P. So again, you have a decomposition of the direct sum of a Burnside group. But again, you can focus on those pieces where that cohomology is present. So, and there are other, any stable birational invariant that you can think of, I don't know, like H3, anything you like, you can put in, and relation B2 will preserve it. So that leads to very interesting decomposition. And in fact, already in dimension 3, you can get very many pieces in the decomposition that will play a role in when you try to distinguish them concrete actions. And in particular, the example that I explained before, the incompressibles, there's just one piece in that decomposition. It just says you don't get it by log, you can put like that. Just one little piece, the disordered piece. But you can carry these things along for all the other pieces. So to summarize, well, ideas from p-adic or motivic integration produce new invariants in equivariant and standard birational geometry. And so now that we have these invariants for 2-3 years, we start looking at all kinds of actions, and we find more and more interesting different classes of actions that are not distinguishable by old invariants, but distinguishable by two invariants. And so we continue to explore the range of applicability of these new invariants. M06, the Burkhardt-Fortek, there are many other very symmetric rational powers equal that one can look at. And another thing is that there is this very rich algebraic structure that we really don't fully understand. And I think I explained to you on some previous occasion when we record only maximal stabilizers for an abelian group, and to look at group generated by symbols and relations to get into homology of arithmetic subgroups of GL and Z. Because I expected. So pure algebraic results like this are also you also have the in some cases. That's it for me. Thank you so much.